Okay, this is a practice problem for the first homework problem, and also my first time recording, so let's see how this goes. Alright, so this is a system, 3x double dot plus 20x dot plus 27x equals 0, and I'm asking you to find the time constant and the frequency of oscillation, if applicable, and also how long it takes for the free response to disappear. So we'll go in order. With these problems, the first thing you want to do is find the damping ratio. So zeta is, what is it, c over 4 square root of mk. In this case, your zeta is going to be 1.11. So that's an overdamped system, right? So overdamped, that means there is no oscillation. So right away that tells you that the frequency of oscillation, it's not applicable in this particular example. So there's no frequency. However, there's still a time constant, so let's figure out what that is. For something like this, you might as well write down the natural frequency, which might come in handy later. Square root of k over m. In this particular case, it's going to end up being square root of 9, which is 3 radians per second. Okay, so the next thing we need to do is find the time constant, and that's going to come in from the roots. So let's go ahead and find those. So remember the roots, I'm just going to actually call them s equals, what is it going to be, minus c plus minus square root of c squared minus 4mk over 2m. So when you do this all out, you're going to end up with these two roots. S is going to be equal to minus 3.3 plus minus 1.453, which is going to be basically two roots, right? So R1 is going to be negative 4.786, and R2 is going to be negative 1.88. So we have two roots. And let's talk about this time constant thing for a second. If you remember, in that underdamped case, which is not what we have, you're going to have two roots like that, complex conjugates. And I told you that the real part is going to be zeta omega n, which is also 1 over tau. That's the time constant. If you have a critically damped case, it's going to be the same thing. You're going to have two roots on top of each other like that, and they're still going to be at the same distance away from the imaginary axis, so that's also going to be 1 over tau. But in this case, we have actually two distinct real roots, and the question is, which one is the time constant? Well, each one of these two roots has its own time constant. So this is going to be 1 over tau 1, this is going to be 1 over tau 2. So that kind of makes sense because, okay, whatever, I just drew that. That kind of makes sense because if you remember the response of this guy, of an overdamped system, looks like this, A1 e to the R1t plus A2 e to the R2t, right? So it's an addition of two exponentially decaying functions. So which one dominates the response? It's always going to be the slowest of the two. And this one happens to be the slowest one because it's going to be 1 over 1.88. That's going to be about 0.532 seconds. If you do the same thing for this one, it's going to be 1 divided by 4.8, which is more like 0.2 seconds. So it decays a lot faster. So this one goes away while this one is still decaying. So the overall system is really dominated by the slowest of the two roots. So I'm going to do a little trickery right here. Just move this out of the way. Just make some room. And so we know this is tau right here. And the question is, how long is it going to take for the free response to disappear? For this example, or for this type of problem, I'm telling you, consider disappearance. I'm going to write this down. Disappear at time is equal to about 4 tau, because that's when the exponential decay kind of goes, at 4 tau, you end up with about 2% of your original amplitude. So anyway, 4 tau is going to be about, if you multiply that by 4, you're going to get 2.13 seconds. So that's your answer for the time of disappearance. And I think that's it, right? So that there's tau when it disappears, and the frequency of oscillation, there's no oscillation, so that's going to be your answer for the third part. All right. Oh, and a quick edit. I think I kind of raced through this part, but you have the 1 over tau 1, 1 over tau 2. Where did this 1 over 1.88 come from? It's simply because 1 over tau 2, or 1 over tau is the real the part. So these are both real roots. So this is your entire real part for the first root. This is your entire real part for the second root. So their time constants are simply going to be the inverse of that real part. That's why I just divide by 1.88 for this second root. Okay.